So in the previous video, we have found out the equation of motion of simple harmonic oscillation. So what was that? The equation of motion of SHM. Well, we have written it as x double dot plus omega squared times x to be equal to 0. Now in this video, we are going to find out how to solve this equation of motion. Okay? So, do you remember how to solve an equation of motion? As you can see, the equation of motion is a differential equation, right? So, in order to find out its solution, you may think that we have to integrate this equation. Actually, in many cases, that is what we do. So, let us remind what we do in case where the force is constant. So, let's take a slight digression. So, let us consider a situation where you throw an object from a certain height, okay? So, this is that height, and you throw an object from here at this angle with some velocity, okay? Let's say the velocity vector here is v0, okay? Now first, let us find out the equation of motion for this situation. Now, if we ignore the air resistance, you can see the only force acting here is gravity, which can be considered a constant force in the downward direction, okay? So the constant force in the downward direction here is the mass of that object, m, times the gravitational constant. And there is no other force acting here, so the force in the x direction is actually equal to 0. So we can write summation of F in the x direction is equal to 0, and summation of F in the y direction is equal to minus mg, where minus means that it is acting in the downward direction, okay? So if we expand it, well, we can write force as m times acceleration, so mass m times acceleration in the x direction, which we can write as d squared of displacement in the x direction, dt squared, okay? So this is fx, which is actually equal to 0, and here you can see for fy we can write m times d squared of y dt squared, which is equal to minus mg. So these two are the equations of motion for this object here, okay? Now we want to find out the solutions of these equations of motion. You can see here this is a double derivative with respect to time here as well, okay? Now we have to integrate this twice with respect to time. Now here in this equation you can see the mass cancels out because there is 0 on the right hand side, okay? So if we take the first integral, we should get dx over dt, and here will be a constant. We can call this constant c1, okay? Now if we integrate this further, we should get x, and on the right hand side we should get c1 times time plus another constant of integration, c2, okay? So now similarly we can find out the solutions of the equation on the right. Here you can see the masses cancels out, so let's take the integral. We get dy over dt to be equal to minus g times the time t plus a constant of integration. Let us call that C3. Okay, now let us integrate it further. Then we will get y, okay, which will be equal to here g times, if you integrate t with respect to t, you get t squared over 2, okay, plus C3 times time plus C4. So our solutions here are almost ready. All you have to do is find out these constants C1, C2, C3 and C4. Now what is this constant C1? Well, as you can see from this equation, this is the velocity in the x direction, dx over dt. Okay, so if you take the x component of this velocity, which we can denote as v0x, this is your C1. Again, remember that this velocity in the x direction doesn't change because there is no force in the x direction. Okay, now what is this C2? Well, from this equation you can see at time t equals 0, C2 is equal to x. That means it is the x coordinate of the initial position of this object. Okay, so if we know the coordinate here of this object, you will know this C2 as well. Again, what is this C3? Well, you can see from this equation that at time t equals 0, this is the y component of the initial velocity. So if we take the y component here and denote it with VOY, then this is our constant C3. Of course, these are valid if we consider this is to be the x-axis and this to be the y-axis. Now, what is this constant C4? Well, again you can see at time t equals 0, it is equal to y. That means it is the y coordinate of the initial position of this object. Okay, so if you consider this position here as your origin O, then this will be the y coordinate, right, which will be equal to this constant C4. Okay, so this is how you find out all the constants using the initial conditions, which ultimately gives our solutions to the equations of motion. Okay, now if you see a little carefully, you will see that these equations of motions or solutions of the equations of motion here and here, they're nothing new. They're just x equals vt and y minus y naught equal ut minus half gt squared. Those formula you should be familiar with, right? Okay, that's all with our digression. Now let's get back to our problem, which was solving the equation of motion of simple harmonic oscillation, this one. Okay, so now what do you think? How should we approach? Well, you might think that we should approach this problem like this one, a typical kinematics problem, right? So let us start in that way. Now let us try to apply the same procedure here. Okay, so let's say we want to integrate this equation of motion in order to find x, right? So you may think we should integrate this thing. Okay, so let's try that. So if we integrate x double dot, it's the second derivative with respect to time, so we should get x dot, okay, plus omega squared, well, this is a constant, times, if you integrate this x, well, it should give x squared over 2, right? And here is 0, so you should get some constant. Now you can integrate it further and you will get x. Okay? But wait, there is something wrong. Here, we have done something wrong. We have integrated this quantity with respect to time and this quantity with respect to x. But we can't do this, right? You can either integrate the whole equation with respect to x or with respect to t, but not this one with respect to t and this one with respect to x. Okay. So this equation is wrong, so let's cancel it out. Okay. Now, if you want to integrate the whole equation with respect to t, well, you'll get x dot here, but wait, you don't know the explicit time dependence of x so that you could find out its derivative, the integral of this with respect to t, right? In order to do that, you need to know x, but we want to find out x here. So you see the problem? It means in order to find out the solution, we need to know the form of the solution. Now, how can we solve this sort of equations? Well, we have a way, and that way is we usually guess. Okay? You heard it right. We usually do guessing. In physics, we call it some educated guess or even Ansatz. Ansatz is the German word for guess. Now, if you take physics as a career, you'll see in future that we have to do a lot of smart educated guess or Ansatz. Okay? So let's try to find the solution of this equation of motion by guessing. For that, let us write this equation motion in a little bit more convenient form, like this. So now let's start guessing. Well, what kind of function, if we take its second derivative, returns that function, maybe multiplied with some constants or something. Okay, so let me repeat. What kind of function that you can think of, if we take second derivative, returns that function multiplied by some constants or some sign. Okay? What happens in case of sine function? Okay? So if you differentiate sine once, you should get cosine, and if you again differentiate cosine, you should get minus sine. So you see, we get the same function with a minus. Okay? Now, if sine satisfies this equation, cosine should too, right? You can try with that. So if you differentiate cosine, you should get minus sine. Okay? And if you differentiate minus sine, you should get minus cosine. So again, we just get that minus and the same function. Okay? So sine, cosine both satisfies this equation. Now, can you think of any other function? Well, what about the exponential function, e to the x or e to the t? Well, as this is the derivative with respect to t, let's take e to the t. Now, if you take its first derivative, what should we get? Well, we should again get e to the t. And if we take the second derivative, we should again get e to the t. So you see, it gives back the same function. Okay? So maybe we need to have a minus sign in front to match this thing, or some constant to match this omega squared. But in general, these are the forms that satisfy this equation of motion. Now, is there any left? Well, actually, there is one thing left. That is x equals 0. You see, if you start with 0, you differentiate, you get 0, you take second derivative, you again get 0. So it's 0. X equals 0 is a solution of this equation too. Now let's write down these solutions in a more general form where it can be applicable as a solution. So a more general function of sine which satisfies this equation, we can write that as some constant a times sine of time, because we have the derivative here with respect to time. So time, maybe we can have some constant in front of that plus a constant too. So this is a more general solution which involves the sine function. Again, we can write down a similar solution by using cosine. So we'll have a constant again, cosine of another constant times time plus c. And a more general exponential function, which is a solution of this equation of motion, we can write that as a constant a times e to the power some constant b times t plus another constant c. And the fourth one is actually 0, okay? So these equations are a more general form of the solution of this equation of motion. Now the solutions are nearly ready. All you have to do is find out these constants a, b, and c. So let us plug this value of the solution in this equation to find out these constants. So let's take the first one as our solution. So we'll write it to be equal to x, the solution. Now, in order to put this thing in this equation of motion, we have to take the second derivative with respect to time, okay? So we can write down the left hand side of this equation to be the constant a. If you differentiate with respect to time, you should get cosine, and the double derivative should give you sine back, but with the minus sign, so we'll have minus sine. Well, as there's a constant in front of t, so you should get b here for the first derivative, and for the second derivative you should get b squared, okay? And here bt plus c. And at the right hand side you should get minus omega squared, which is constant, and you just simply put this value of x, which is a times sine bt plus c, okay? So let's see what we can find out from this equation. Well, as you can see, this a and a cancels out, minus minus cancels out, okay? These two are the same, so they will cancel out too. So we'll have b squared to be equal to omega squared, okay? So that means b squared is equal to k over m. You remember the definition of omega, square root of k over m, okay? Now this is how we find out the constant b, right? From now, this constant b depends on k and m. K is the spring constant and m is the mass of the object, which is oscillating, right? So this b should be a constant, right? Which depends on the properties of that system, right? But what about the constants a and c? Well, we could not find any value here, right? So that means that this a and c can take any value for a given equation of motion. Later, you will see that we can associate this constant b with the frequency of the simple harmonic oscillator, this constant a with amplitude, and this constant c with the phase. Now, the amplitude and phase, if you vary them, actually the equation of motion remains the same. So we can have the same equation of motion for different amplitudes and even different phases. But if you change the frequency, that means if you change this constant b, well, you will have a different equation of motion.